the component form is equivalent to the vector form. So we use the component form. That's enough. We get its components. It's equivalent to that. We get the whole vector, the direction, and for the acceleration, so that's dv over dt. So this part corresponds to dvx over dt, while this part should be dvy over dt. And vx should be this one, and vy should be this part. And you can substitute this in this part here, and this part to here. You will arrive at this two. So so that means vector kinematics or kinematics in 2 dimensions. We just resolve it into components and change this kind of problems into like several problems in 1 dimension. Okay, and for just checks, we have showed you that all the equations in 1 dimension can be applied to 2 dimensions for each component. And when we compare this, the equations for the x and y components, that should be exactly the same as the equations in kinematics in 1 dimension. And this is for constant acceleration, and for all the other motions, that's the same. That's the same. Okay. So, okay, let's. So in chapter 2 and 3, we investigated how the thing moves, how they move. So that is kinematics. And in chapter 4 and 5, they're about what we call mechanics, or especially the dynamics. So dynamics is different from kinematics. Dynamics, it tells us why the objects move like this. So the kinematics tell us how they move, and it help us to predict their motion. And dynamics tell us the reason why they move like this. So there's a difference between dynamics and kinematics. So Newton's laws can help us to understand why they move like this. So sorry, I'm afraid it's missing. Okay. Why this? No, it's not. Okay. So this is a very famous book, which is called Principia. Originally, it's not written in English. It's used in Latin, because at that time, Latin is the language that they use in academic world, like that. But at that time, English is not that widely used. So this is a book written by Isaac Newton, and it's a very famous book. And in this book, it describes tells about the calculus and the Newton's laws and the gravitational laws. So in this chapter, we are going to investigate these topics about the force and Newton's laws, and how to solve problems with Newton's laws. So force, so is it can help us how to explain why the things are moving like this. So we need the definition of force, but actually we do not know what is the force at that time. But we know, okay, I push this, I apply force on this object. We know we can describe this is a force, but we cannot describe the force with like scientific definition of force. We just know a rough image. What is the force? I push this, I will apply force on it. We know that is the force, but there is no scientific description of what is the force. So force, in Chinese, we call it li, force. So dynamics investigate the connection between the force and the motion. So that is why in Chinese we call dynamics 动力学. So 动 means motion, 力 means force. So 学 that means laws, like this. So 动力学, dynamics, that's the connection between force and motion. The force in Chinese is 力. So it is a vector, because we know the force as magnitude and direction. And the unit is Newton. So because in honor of this guy, Isaac Newton. So, but as we mentioned, what is a force? We know we push some object, that is a force. But we need a scientific definition. So in order to define the force, we actually need Newton's laws. So this is the first law. Every body continues in its state of rest or uniform speed in straight line as long as no force acts on it. So, now we know this should be correct, but at that time, not everyone agree with this. Not everyone. Just like here. They agreed with this continued state of rest. They agree with this because even at that time, people know, okay, we do not push this object, it will not move. It will be at rest if I do not push that. So they agree with this. It will be at rest if there's no force on it. But they didn't agree with the second part. It can keep uniform moving in straight line with uniform speed when there's no force on it, because they believe, okay, if I do not push it, it will not move. If I let it move with constant speed in a straight line, I must push it. Then that means I apply the force on it. So they do not agree with the second part. It can keep moving with constant speed in a straight line. But what they didn't realize is that they ignored the friction. They didn't realize there is friction. So why I have to push it to make it move in straight line with constant speed? That's because of friction. When it is moving, there's friction. So Galileo carried out an experiment to show the others if there's no friction, it can keep moving. So his experiment was like this: a slope and a ball fall from the slope, and he changed the substance here from very rough surfaces like the sand, and then switch this part to be glass. So he found that with sand it can move like here and here, but if we put the glass here, it will move to very, very far away. So Galileo concluded that, okay, if here is a surface with this very perfect surface, there's no friction, it can keep moving. So based on Galileo's experiments, Newton generalized this first law. So it can keep on moving if there's no force. So keep on moving at uniform velocity does not require let force. If it is originally at rest, we want it to move, we need a force. But if it is moving and we want it to keep on moving like this, there's we don't need a force. We don't need a force to keep it moving. So that's what Newton's first law tells. And Newton's first law also tells us another thing which is called inertia. In Chinese, it is called 惯性, the tendency of a body to maintain its state. Everything has this inertia. It's just like a property of everything. Everything tends to keep its state of motion. Yeah, someone asked me, this law is almost impossible in life. Yes, almost, but it is true because when you are in this space, far from the planets and the stars, there's almost no force on it. So we can test that. And another thing is that as long as no let force here, no let force, which makes it possible in our daily life. Because here is no let force does not mean no force. No let force means there can be several forces on this object, but the sum is zero. Just like, for example, here is a rough surface, and I apply a force on it, and there will also be friction in the opposite direction if I let it move in this direction with velocity v. And if F is equal to the force I applied on this object is equal to the friction, the net force on this object should be 0. So that is equivalent to no force on it. So this object will keep on moving, and it does not require an extra force. So remember here, no net force does not mean no force. So there can be several forces on this object, and the net force, the total force on this can be 0. So this makes it possible in our daily life. Even on a rough surface like this, the friction is inevitable, but we can apply force on it, and this makes the net force can be 0. So this is possible in daily life. Okay, so inertia 惯性 is a property of everything. Everything wants to keep its state now. So everything wants to keep its state now, just not the motion, but just like if the environment is convenient for you, you want to keep that, right? And so everything tends to keep its state, and this is called inertia or 惯性. So, okay, if we know the Newton's first law, actually we can explain this. A school bus comes to a sudden stop, and all the backpack here on the floor start to slide forward. So the question is, what force causes them to do that? And also maybe when you are on the bus, if there's a sudden stop, you tend to go forward, right? And you need to grab something so that you will not fall to the ground. So what force causes them to do that? Okay, so actually it isn't the force does it. According to Newton's first law, the backpack continue their state of motion. So the bus suddenly stopped, but you and the backpack will keep on moving. So they want to keep their velocity. They do not want to stop. So that's why they will move forward. But actually, they will not move with constant speed because of friction on the floor. So they will finally stop, but they will move forward. But if it is a frictionless surface, it will keep on moving. And that's the same reason why you will go forward. And you need the extra force to stop that. If there's no extra force, you will keep on moving. You will move forward. So it isn't the force that does it. It's the inertia. Everything wants to keep its state of motion, or maintain the velocity. So you will, even the bus stops, you want to move forward. You still want to move forward. Okay. So now we believe that Newton's first law should be correct. But someone may not agree with that. Still may not agree with that, just like here. Two guys, one is on the floor, on the ground, and the other for example, on a tree, like this. And we can assume that here this surface is a smooth surface without friction. We can assume that. If we assume that, let's see what will happen when this train accelerates. So when this train accelerates, you can see here this ball moves to this guy. But the when we consider this guy relative to this guy, it does not move, right? Still here, relative to this guy on the ground. So let's check this again. So originally the ball is here relative to this guy, right? And when it accelerates, it moves to this guy, but relative to this guy, still at rest. So for the guy on the ground, he believes that Newton's first law is correct because there's no force on this object and it keep at rest. So he believes that Newton's first law should be correct. But for this guy, he does not think so. He believes that there's still no force on this guy because it's smooth surface, and in the vertical direction, maybe the normal force and the gravity they balance each other. So there's no net force on this object. But why originally it is at rest and now it is moving? Why it start to move toward me? So the guy on the train, he does not believe the Newton's first law is correct. So that means that Newton's first law does not always hold. There should be requirements, or Newton's first law holds only in special substitutions, like this. When, or in what kind of requirements is this the reference? We can see the difference between these two observers as they choose the different reference. And this guy choose the ground as the reference. And this guy choose this accelerating train as the reference. So that's the difference. So that means in different reference frames, Newton's first law will not always hold. It holds only in initial reference frame. The reference frame in which the Newton's first law holds is called initial reference frame. Or we can, so this definition cannot help us to determine which reference frame is initial reference frame. So we need this explanation to help us to determine which one is initial reference frame. The reference frame fixed on a body which has no acceleration or has no force on it. No net force would mean no net force. Or net force on it is 0. For example, here in this classroom, the desk originally at rest, right? The desk at rest. The desk has no acceleration relative to the ground, and the net force on this desk should also be 0. And if we choose this desk as a reference frame, that is a initial reference frame. And if we choose the ground as a reference frame, that is also an initial reference frame. But if you choose the train, that is not, because the acceleration of this train is not 0. So that's the initial reference frame. And usually on the Earth, we can choose the Earth as an initial reference frame for most of the problems. But when you are dealing with the L movement in the atmosphere, you cannot treat the Earth as a reference initial reference frame because it's spinning. But in the most of the case, if we when we discuss the motion of the object on the Earth, on the surface of the Earth, we can treat it as a initial reference frame. So Newton's first law is only valid in initial reference frame. So, but there can be several reference frames in which the Newton's law holds. This reference frame, this initial reference frame is not the only one. There can be several initial reference frames. Any reference frame that moves at a constant velocity relative to an initial reference frame, that is also an initial reference frame. So that's why if we treat the Earth as an initial reference frame, the desk at rest on the surface of the Earth, it is also an initial reference frame. So you can choose any reference frame which moves at a constant velocity relative to the Earth. So anyone is okay. It depends on which one you feel that's convenient. And the reference frame in which the Newton's first law does not hold, that's long initial reference frame. For example, that train. Some object is moving with non-zero acceleration on the surface of the Earth. Or something is rotating. Something is rotating, and you choose that object as a reference frame. That is not an initial reference frame. Something is rotating and something is accelerating. They cannot be chosen as an initial reference frame. Okay, that's the first law. The first law tells us everything wants to keep its state. But if everything wants to keep its state, that's not so good because sometimes we need them to change. So if you want to change the state, just like if it is moving, you want to stop it, we need a force. So Newton's first law is about the case when there is no let force. But what if there is force? There can be several forces on this object. So that's something need to be explained by the second. But before we discuss the second law, we need to discuss. Before that, we need to know something like the mass. The mass in Chinese is called 质量. According to Newton's original explanation, he defined the mass as the quantity of matter. And what does the quantity of matter mean? It actually means the measure of inertia of a body. So why the mass means the quantity of matter or the measure of inertia of a body. So that's reasonable because according to our daily life, if something very heavy and it is moving, you want to stop it. It's very hard, right? But if something light and is moving with same speed, you want to stop it, that would be easier. So that means the heavier things, it's not so easy to change its state of motion. But light things, you can change its state very easily. So maybe we know heavy means more matter. That means heavier object has greater mass, and it is not easy. It's not easy to change its state of motion. And inertia means they want to keep its state of motion. It's easier. It's not easy to change. Means it's easier to keep, right? It's not easy to change. Means easy to keep. So that means heavier object tends to keep its state of motion. That means heavier object has greater inertia. So that's why we say the mass is the measure of inertia. It's the measure of inertia. And you need to know mass is different from weight. Mass is the measure of inertia, while weight is a force. It's a force near the surface of our Earth on this object. Okay, let's take a rest. We'll go on after 5 minutes. And this is the attendance for the fourth one and the next one. So you can also use this week because according to the SIE, they ask us to do this twice each time. So this is for the second time. So we are asked to check the attendance twice each time, right? So, and this is for the second time. If you haven't do that, so be quick. So you can do that quick. Okay, so to get this. Okay, put it back. Okay. You can do this after, like, I give you 1 or 2 minutes. Okay, so let's go on. Okay. So mass in Chinese we call it 质量, but weight is different from mass. Weight in Chinese is called 重量. So mass and weight, they are different. Mass is the measure of the inertia of a body, while weight is the gravitational force on it near the surface of the Earth. So this is a force, and this is not a force. And they do not have the same quantity. For example, if we use m, okay, sorry. So if I use n to indicate mass, and near the surface of the Earth, weight is equal to mg. G is the acceleration of free fall object near the surface of the Earth, and g is equal to 9.8 meters per second squared near the surface of the Earth. So these two, they are not the same. Mass m and weight is mg. Weight is a force, while mass is the initial of the measure of the initial of the object. So that's why we we can call it initial mass because it's the measure of initial of a body. But usually we call it mass for short. Okay. After we defined the mass, we can go a step further. That's the Newton's second law. The acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. The direction of the acceleration is in the direction of the net force acting on this object, and we can use a simple equation to help us to describe this Newton's second law, which is F is equal to ma. Maybe you are familiar with this equation. The force, this is the force, and is equal to the mass times the acceleration. So the force is proportional to the mass, and the acceleration is proportional to the force, but the acceleration is inversely proportional to the mass. So and they have the same direction. If we write this equation in a vector form, we can put an arrow on this force and put an arrow on this acceleration. That means, and m is a constant for a specific body, so that should be the same direction. But this equation actually is not the original form of Newton's second law. So the original description by Newton is something like this. The alternation of motion is ever proportional to the motive force impressed and is made in the direction of the right line in which that force is impressed. So here, the alteration of motion, Newton, when Newton explained this, he said it should be equal to mv, the mass times the velocity. That is called the alternation, the alternation of this, alternation of mv. So alternation of motion is alternation for mv. So if we use the language of calculus, this force should be equal to dmv over dt. It's different from this one. This one is equal to m dv over dt. So this one is equal to this one only when the m does not change, the mass does not change with time. So this one is more general, while this one is practical in our daily life. So this is the equation for Newton's second law in 3 dimensions. In 3 dimensions, we can use the complex form because force is a vector. We can use a complex form. That's the second law. So second law, actually, it helps us to know what is the force, because we have defined the mass, and we already know what is the acceleration. So according to Newton's second law, what is the force? Force is the mass times the acceleration. The mass times the acceleration is the force. So that helps us to define the force. And now we do not use this to help us to measure the force. Usually we use 3 to help us to measure the force. And if we know we can measure the force, and still this F is equal to FA, can help us to measure the mass. So why we need to use this equation to help us to measure the mass? Because maybe when you want to measure your mass, on the surface of the Earth we have certain equipment, right? It does not based on this equation, because we know on the surface of the Earth the mass is proportional to the weight, right? So actually we are measuring the weight on the surface of the Earth. But this method will not work when you are in the space. So in the space, we need to monitor the mass of the astronaut to make sure they are healthy. We must monitor the mass of the astronaut every day. But on the in this space, the weight meter will not work. You put anything on that weight meter is zero. So in this surface, how can we know the mass of the astronaut? So we actually had a certain device, if this is some device and this is something, and something like a device like this, and put the astronaut here, and then we release this part, and it will move in this direction. And actually, this device can apply a constant force through this part on this astronaut. And we measure the acceleration. Then we measure the acceleration of this astronaut. We know this constant force, and we measure the acceleration of this astronaut, and this can help us to calculate the mass. So that's how we measure the mass of the astronaut in the space. And this is based on Newton's second. We do not use this device on the surface of the Earth because we can use weight. We can measure the weight, but in the space you cannot measure the weight, because that you use a weight meter to measure anything, that's zero. Because in this space that's zero weight, right? Okay, that's the second law. And the third law, and maybe most of you are familiar with this, is whenever one object exerts a force on a second one, the second object exerts an equal and opposite force on the first. So if we use a equation, that's F12 is equal to minus F21, which means in the opposite direction. So this one is very simple. So, and you all know this, so we will not focus on this one. Okay, so we have introduced three laws, and when we want to apply these laws to the real problem, we need to know the different kind of forces, the feature of the forces. If we want to use that, for example, the second law, F, so the force. So we want to know the feature of each force so that we can use the right equation instead of a simple letter F in that equation. So in this section, we are going to investigate the forces in mechanics. We start with this one, gravity. Gravitational force and gravity. So we know the equation, gravitational force. The force is equal to G m1 m2 over r squared. This is a gravitational force. And gravity, we mean the almost gravitational force near the surface of the Earth, but slightly different. But for example, the gravity actually consists not only the gravitational force, but also the effect of the rotation of the Earth, of the spinning of the Earth. But usually we can write it like this: gravity near the surface of the Earth, m is equal to mg, but only near the surface of the Earth. Only near the surface of the Earth. So, and when we are very close to the surface of the Earth, these two is almost the same, the gravity and the gravitational force. When on the surface of the Earth, they are almost the same, but slightly different because of the spinning of the Earth. So on the surface of the Earth, these two, we can treat it almost the same as an estimation. So, but when we talk about gravity, we know F is equal to mg, but according to the Newton's second law, if the object has acceleration a, F is equal to ma. For a free fall object, these two should be the same force. So if these two are the same, we can arrive that here ma is equal to mg, then we can cancel the m's, so that a is equal to g. But according to Newton's second law, this m, it means the measure of the inertia. But according to this equation, this is the gravity. So according to this equation, this m is the measure of gravity. The heavier the object, the greater the m, because g is constant. So which means these two m's, actually they are not the same. The m on the left-hand side is the measure of the inertia, while the m on the right-hand side is the measure of gravity. Actually, we should not use the same sign. So we call this the initial mass, while we call this one gravitational mass. There are different physical quantities, but in our daily life, when we cancel these two, it's a correct conclusion. It has been tested. Okay, what does this mean? This means the number of the pages for the hard version of the book. But if you do not use the hard version of the book, you can ignore this. Okay, are the UMs happen to be equal? Because they are equal to each other. Because this conclusion is correct. It has been tested several times, many times. So Einstein says, no, it's not happen to be the same. They should be the same. They are different quantities, different physical quantities, but they should have the same value. So that's something interesting. So this is called the principle of equivalence. This is called the principle of equivalence. It's one of the fundamental assumptions of the general theory of relativity. So we'll discuss this later in next semester when we discuss the relativity. So gravity is one of the forces. Why we explain gravity first? Because you can never escape from gravity, right? You will never escape from gravitational force. No matter how far away the two objects are, there will be force between them. So no matter how far away the objects are. So there will be gravitational force between them. So that's why we discuss this first. It's a universal gravitational force. So you cannot escape from this. So why we say it's universal, because you cannot escape from that. And Newton, at that time, Newton realized that something is falling and something is go around the Earth, like the moon and the apple fall from the tree to the Earth. Actually, that's the same kind of motion. So why they are actually the same? So we can explain that. So why they're actually the same? Because the force on them are the same. So just like this is the Earth, something apple fall to the Earth, and the moon go around the Earth. According to Newton, these two motions should be the same. What's the difference between these two? Okay, we can see it like this. When you throw something, with greater speed, it will go further, right? Okay, that's on the flat surface, but our Earth is not flat, right? It's like a spherical surface, like this. And if you throw something, it will go further, and throw with greater speed, it will go even further. But it's a spherical surface, a curved surface. So if we throw it with very large speed, it will fall, but it will not on the surface because it's a curved surface, right? And it will go on moving. It want to fall, but it cannot fall. It will go around the Earth. So the difference between the apple and the moon is that they have different horizontal directions, horizontal velocity. It will directly fall to the Earth if there's no if it is zero velocity, it will directly fall to the Earth. But with small velocity, it will fall to some place further. And if you have enough velocity in horizontal direction, you can move around the Earth. So that's why if you want to launch a satellite, you need to make sure it has enough speed so it can go around the Earth, not fall to the Earth. If the speed is not enough, no matter how high we release it, it will fall to the ground. So that's the difference between the moon and the apple. They are different in the horizontal speed. Okay, so that's the gravitational force. And there are other forces, like the force on a spring. If the spring originally is like this, and we put it here, a displacement of x, the force is equal to minus kx. And x means the displacement relative to the equilibrium. Where it is minus sign means the force is in the opposite direction of the motion. So this is one kind of elastic force, the force caused by the change in the shape of solid. When you change the shape of this spring, it wants to go back to its original position. So in this case, the force appears because of this. And the elastic force is not only the force in the spring, but also like this. If you use a rope to drag this block, this tension, the tension in the rope is elastic force. It's a kind of elastic force. Because you use this rope, the rope wants to be longer, but it will go back to its original length. So that's why the tension appears. And the normal force, the force on this block due to the contaction between the force and the surface, the normal force is also elastic force. So normal force, tension, they are also elastic forces. So that's there are many kind of forces. There are elastic forces. The force caused by the change of the shape. It want to go back to its original shape. So that's elastic force. And actually, friction, you can understand friction as a microscopic elastic force. It's almost the same, but slightly different. Okay, we know the gravity, and the elastic force, and the force due to the also the friction, and maybe the drag of the air, like that. So all these forces are the forces in our daily life or in mechanics. But if we use in the physics, the force in the physics, we have only 4 types of interaction. And there are only 4 types of interaction have been found in the universe. The gravitational interaction, we mean the gravitational force, and electromagnetic interaction. Actually, the elastic force is one kind of electromagnetic interaction. Why? Because the elastic force is because of the change of the shape and of the solid, and the solid wants to go back to its original shape. That's because the force between the molecules, the electrons and atoms, between the electrons and the atoms, the electric force between them. So that's why the elastic force actually is the electromagnetic interaction. And these two, the strong interaction and the weak interaction, only appear in subatomic scale, which means inside the nuclei. So we have found only these 4. The first 2 at any separation, and these 2 only inside the nuclei at some subatomic level. So this is the force in physics. So in previous section, we discussed the force in mechanics. There are 2 ways of we sort the force into different types. But so that's it, from different perspectives. Okay, in order to modelize a real problem, usually we need to use the free body diagram. The free body diagram is a diagram that can show all the forces acting on each object of the system. So if inside this system we have 2 objects, we need to draw the force on each object, on both of them, separately, not as a whole. So we mean we need to show the force on each object of system separate, not put them as a whole. The second step, we need to resolve the forces into components on X and Y, maybe sometimes Z, but usually only 2 dimensions is enough. And for each object, we can apply Newton's laws in x and y components separately, and then we solve the equation. So that's how we solve the problems with Newton's laws. Finally, you should consider whether your result is reasonable. Okay, let's just take this for example. What average force is required to bring a 1,500 kilogram car to rest from the speed of 1 kilometer per hour within distance of 55 meters. So, first step, we need to draw a diagram to show all the forces on this. So, in this case, there's only one object. This car, we treat it as a particle, and all the forces on it, the average force. So this is maybe x direction, and we need to apply a force in this direction f. And maybe there will be force in this direction mg and a normal force n, and they should be balanced, right? They should be balanced. So we only need to consider the force in x direction. That's what we are going to calculate, the average net force. So there's only one force in x direction. There's net force in y direction is 0. So we need only to consider the x direction. So in x direction, F is equal to ma, the average force. So if we know the mass, so if we want to find out F, we need to find out A. So in order to calculate the A, we know the car start from rest to a speed of 100 within a distance of 55 meters. So according to the equations in previous chapters, there is a very important equation which can be applied here. We know that v square minus v0 square should be equal to 2a times x minus x0 square. So this part, x max x0, should be 55 meters. And from rest, so v0 is 0, and v is 100 kilometers per hour, and you need to change it into meters per second. So we know this 100 kilometers per hour. So we can calculate A and substitute A into here, we get F. So that's how we solve this. So first step, we draw a diagram. And the second step, we solve forces into x and y components. In this case, we only need to consider x components. And the third step, we find out the equation for this. So in order to calculate F, we need to find out A. And if we want to find out A, we need this equation from chapter. Yeah, someone has got the answer. We need this equation from chapter. So finally, we can arrive at our conclusion. So if we want to calculate F, so we find out A, and F is equal to ma. So that's how we calculate it. So this one is relatively simple because it's in one dimension, and so the force must be applied in this. Yeah. Okay. This is another apparent weight loss. So a 65-kilogram woman descends in an elevator that briefly accelerates at 0.2 g. So g is 9.8 and downward. So the acceleration is downward. And he stands on a scale that is raised in kilogram. Okay, he's in a elevator which has an acceleration in this direction with 0.2 g, and he's standing on this scale. He wants to measure his weight in, but it is in kilogram. So we need to know how this scale works. So first step, during the acceleration, what is her weight and what does the scale read? So if you use a scale to measure your weight or your mass, you just watch the scale, and thus the scale can usually can tell you your real weight or real mass. So that's about this example. So first, during this acceleration, what's her weight and what does the scale read? So in order to know what the scale reads, we need to know how it works. So, this one stands on the scale, and we can draw the free body diagram on this woman. There will be weight mg, right? And there will be normal force from the scale. So what does the scale read? The read of the scale tells you actually it's not your weight, right? Why it has a readout? Because when you stand on it, actually you apply a force on the surface, right? And you just give a pressure on this scale, and the pressure on this scale, according to the Newton's third law, should equal to this Fn, the normal force on you. The force you applied on this scale should be equal to the force the scale applies on you. That's something according to we can infer this from according to the Newton's third law. So actually, the read of the scale actually is this Fn, not mg. So what's your weight? Your weight is equal to mg. So use this to calculate the weight. But what's the read? That's Fn is the read. So the scale will read Fn. So Fn, according to Newton's second law, mg minus Fn should be equal to ma. So you can calculate Fn. So because ma should be equal to mg minus Fn. And the read of the scale should be equal to Fn, because according to Newton's third law, the force applied on this scale should be equal to the Fn. So if you want to calculate Fn should be equal to mg minus ma. Should be equal to mg minus ma. So which force does the scale tell you? It's not the weight. is not the weight. The normal force that the person exerts on the scale, or the pressure from the person on the scale, that's the force the scale tells you. And according to the Newton's third law, it should be equal to Fn. It should be equal to the Fn, but in opposite direction. So if we know this, we can calculate it. For the weight minus Fn should be equal to ma. While ma is equal to 0.2 g, g is the acceleration of the near the surface of the Earth. And we can calculate that is if mg is your weight, it's only 0.8 times less than your weight. And you maybe you are happy because you say, okay, I'm lighter. I'm not that weight. I'm not that heavy. But it's not the truth. It's not the truth. Okay, and her weight is about this. It should read 65, but now the reading it is a reading of 52. Okay, so this is called apparent mass. Apparent mass. So if it's falling with acceleration g, if a is equal to g, what will happen? The read will be 0. Because if a is equal to g, that means Fn is equal to 0. The scale has no force on you, and you have no force on the scale, according to the Newton's third law. That is called loose weight. That's called loose weight. So if the acceleration is down and equal to g, what's the scale read? 0. So if it's not moving down with acceleration g, it's moving up with acceleration g. What's the result of this scale? It will be twice, right? It will be twice, because if you are moving up with acceleration g, that if you are moving up with g, that equation should be minus mg should be equal to mg minus Fn. So that means Fn should be equal to 2mg. So that's what happens when we launch a spaceship, or when we launch a satellite, or when we launch a rocket. The rocket needs to accelerate. So when it accelerates, the astronaut in it, the force on it will be several times of his own weight. So that's why we need special training for the astronaut on the surface of it, because we need he can survive under that pressure. Okay, so we can stop here today. The class is over.